Welcome back and to this course of electronic packaging and manufacturing, and today we will continue with where we left off in the last lecture. We had just introduced you to what is chip carrier and types of chip carriers. So, today what we are going to cover are ceramic chip carriers and plastic chip carriers. This will be the main focus of this lecture, and then we are also going to go into something called a dual inline package or DIP. It is probably the first type of package that was invented back in almost more than 50 years back, and we will end this by looking at types of leads or types of these interconnections that come out of these packages. Okay. So, with that, let us move on and look at ceramic packages, ceramic chip carriers. So, ceramic packages. So, ceramic chip carriers, as the name suggests, the casing is made of ceramics. Okay. Now, ceramics are not inexpensive, they are expensive. So, the cost of ceramic chip carriers is high. So, we do not use it in everyday use products like your cell phones or laptops or computers. These are used for, let us say, military applications, avionics, okay, which are the high end products. Okay. They are also used for products which have very stringent sealing or hermeticity requirements and very high, and also for high I/O count. Okay. As I said, these are used in high level products, high end products. The bonding material that is used, the bonding material between the chip to the chip carrier and the lead frame, that bonding material here is typically eutectic solder of gold and silicon. Okay. A very expensive material, it is inorganic, so therefore, does not release volatiles. The melting point is very high, so temperature wise it is stable. So are ceramics. Thermal conductivity is high, because remember that was one of the primary heat conduction path from the chip into the lead frame and then through the leads to the motherboard. Okay. So, high thermal conductivity is important. So, 296 watts per meter Kelvin is actually a very high thermal conductivity. To give you an idea, thermal conductivity of copper, which is one of the best thermal conductors that we come across in our daily lives, that is 400 watts per meter Kelvin. Next, aluminum, its pure aluminum is around 238. Okay, this is better than pure aluminum. The regular aluminum that we use, the aluminum alloys, these are around 180, 200 kind of stuff, watts per meter Kelvin, that is. So, this is way better than that. So, as a result, as I already said, that this high thermal conductivity helps in the transfer of heat from the chip to the casing. Okay. So, these are ceramic chip carriers. Okay. Once again, I want to mention that it is made of ceramic. Ceramic is not a cheap material. So, these are extremely expensive packages, extremely expensive first level packages, and not used in commodities, in what should I say, when in high end or high use products. Okay, like your cell phones, laptops, they do not have ceramic packages. Okay. These are used in very high end products. All right. So, if you look at a ceramic package, so let us spend a few minutes on this slide. This is the assembly process. Okay. We will see a similar one for plastic packages as well. So, if you look over here, the first thing what you see over here is the lead frame. Okay. So, the lead frame looks like this. So, different leads are coming out from a central podium, if I call it so. It is branching out, okay, and this is where the die or the piece of silicon or the chip is going to come and sit. Okay. Then this is going to sit on a base which is aluminum Al2O3, that is the ceramic. All right, and this is how it is. Now, the die is connected, and the connection, as we saw before, is done by a bonding material which is an eutectic solder of gold and silicon, right, with very high thermal conductivity. So, that connection is made. So, the chip attachment, which is the next step, is done. So, the chip is over there, the leads are also there, but then I have to connect the two, and the way that is done is through this aluminum wires. So, these wire bonds that we saw in the picture, remember in the first picture when we saw that in the previous lecture, the very basic configuration. So, these are those wire bonds, probably you can see them over here. The picture is not very clear, but you should be able to see these wire bonds, which is coming from several points, different points on the chip, and to these leads that are coming out. Okay. The next thing that we do is we put the lid or the cover, LID, lid or the cover on top, and then we seal the sides using some glass sealant. Okay. And this is how, therefore, the package finally looks like. And then what we will do is we will trim it off, trim off these bottoms, so that you have these pins or leads coming out of this package. So, see what we had started with. We started with a very small piece of silicon, which we are calling the die. Again, die, chip, microchip, microprocessor, IC, piece of silicon, these are all the same things. These terminologies are going to be used interchangeably throughout this course. Okay. All right. So, that was my starting point, this die, the piece of silicon, and this one is my finished product. Not, well, I will not say finished product, this is a finished package. To make it product, this package now has to be connected to a motherboard to a connector, connected to a system and all that. So, then finally, you get this product, but finally, this is the package. So, outside what do I see? Outside I will see a rectangular box made of ceramic and with some leads coming out from both sides. But inside, if I am able to scrape off the top layer and able to see inside, this is what I am going to see. I am going to see a piece of silicon sitting inside. All these leads actually are connected to a lead frame, and then I will have these thin delicate wires, typically made of gold, connecting the various points on the piece of silicon to these leads. Okay. So, once again, let us recap what we just saw, this assembly process. We start with the lead frame and a base made of ceramic. The piece of silicon comes and sits on this central portion of the lead frame. Okay. The connections are going to be made from the top surface of the die, okay, and those connections are now done through these wires. These are typically, I mean, I am showing it as aluminum wire, but these days mostly it is gold. Okay. Some of the very low end toys and all probably will have aluminum wires, but once you go, but gold is probably used more often these days. Okay. And then there is a ceramic lid or a cover that comes onto it. The sides are sealed. The leads over here, LED leads, are going to be trimmed off, so that now you have these pins that are coming out, and so these are the interconnects. Okay. These are the interconnects that are going to connect this piece of silicon to the wiring traces in your motherboard. All right. Okay. So, ceramic chip carriers, if you look at it, they can be of several types, as is being shown here. I will just show these names for now, because we are going to discuss them later in more details. One is flat pack. Okay. Flat pack, what is happening? It is flat, the leads are not taking this right angle turn as was shown in the previous slide. Okay. Instead, they just come out in the form of a plane. Okay. So, they fan out in a particular plane, and that is why it is called a flat pack. Okay. Also sometimes called quad flat pack, because the connections are coming out from all the 4 directions. Then there is something called a pin grid array. So, over here you have these pins that come out. Okay. They can be just peripheral, as is shown in this picture, or there can be pins in several rows, as is shown over here. So, that is a pin grid array. So, what I will see is, of course, there is going to be another cover or the lid on top of the second diagram, but once we see that once that lid is over there, the ceramic lid is going to be over there, what we will see is the interconnections are going to be in the form of pins that are coming out from the bottom surface. Okay. And it can be a pin array, it does not have to be just along the periphery, there can be another layer as is shown over here. You can see 4 pins on the outer layer, you can see a few more on the inner layer. Okay. Then there is something called a lidless chip carrier. So, in the lidless chip carrier, what happens is there are these cavities which with kind of a metallized surface inside. Okay. So, again these are classifications under ceramic chip carrier, these are classifications based on the types of interconnections. Okay. And these ones, as you can see, these actually are sometimes even called the J lead carriers. Okay. So, the leads, the interconnects actually turn, I mean it kind of curves and in the form of a J, and that is why it is called the J lead. You see this shape. Okay. So, these are ceramic chip carriers. I mean again some of these are in plastic as well. For example, this one PLCC is plastic leaded chip carrier, but I mean the configuration can be both for a ceramic as well as a plastic package. Okay. So, that brings us to the next slide, which is plastic encapsulated microcircuit or PEM. Okay. This is nothing but plastic chip carrier. Again I am going to show sometimes these different acronyms, because these are widely used in the electronics industry, but what it essentially means is this configuration, which is plastic chip carrier, but the only thing over here is the space inside is typically filled, encapsulated with this material. Okay. And that is why it is plastic encapsulated module or plastic encapsulated microcircuit. Okay. So, what does it do? It consists of an integrated circuit physically attached to the lead frame, electrically connected to input output leads, which is the same as what we have studied till now, and molded in a plastic, that is the important part, molded in the plastic that is in direct contact with the chip. Earlier there was a bottom frame, a lid, but now this is all, everything inside is plastic. So, it is not possible to move the lid and see these connections inside anymore. Okay. So, it gives it more protection definitely. So, but this is used for products with low powers, moderate IO count and lenient hermeticity requirements. Low powers, why? Because plastic is not a good conductor of heat. All right. Next, moderate IO count, because the number of interconnects that can be accommodated in a plastic chip carrier is less compared to a ceramic. Okay. And lenient hermeticity requirements. So, this is important. Plastic, as solid as they may look from outside, always allows for moisture ingress. Okay. So, moisture ingress is inevitable in plastic. So, therefore, with time there will be moisture driven degradations of these connections inside, of these pins, of these wires, you cannot help it. So, that is why a product that is supposed to last 20 years typically will not use plastic material, plastic encapsulated chips. But something that is supposed to last for a few years, like 3 years, 5 years, yes. So, if you look at your computer, the memory chips are all plastic encapsulated, many others, okay, several others. So, what I will do is in the next class, I will bring in some of these some devices and chips that I have in my office, and probably we will be able to see some of them. Okay. So, if you look at this configuration in this picture, the configuration is more or less the same, that parent configuration that we saw in the last class is similar. You have a silicon chip, you have a die attached, what is the lead frame or the die attached paddle, what is called, and then it is connected by some kind of a bonding material. And then you have the lead and the lead frames, and which is connected to these points on the silicon using these wire bonds. The only difference is the bonding wires. Okay. The only difference is you have this molding compound, which is a plastic material, that fills in this entire space inside. Okay. So, that is the main difference with a ceramic in terms of construction. Of course, in terms of materials, IO count, etc., there are lots of differences, but in terms of just construction, the main difference is the fact that this is completely encapsulated by this molding compound, plastic molding compound. Okay. All right. So, similarly, probably a little more detailed, the plastic encapsulated microcircuit assembly flow chart. Okay. We are starting from probably from the wafer itself. The first two are already done, okay, the wafer and then the chip is taken out. Okay. The wafer is first taken, the circuitry is, through all these microfabrication processes, the circuitry is there on each of the silicon pieces or the silicon dies, and then it is diced through the diamond blade to get these chips out. Okay. And then this is the lead frame that I have. The two raw materials have the chip and the lead frame. So, the chip is attached to the lead frame, and then you have this wire bonding that happens over here from the points, the connection points on the chip on the top surface to these leads. Okay. So, all this wire bonding is done, and then this is the one which is important, where it is the encapsulation is done, the mold. It is put in the mold and this entire encapsulation is done, and so what finally comes out is typically black in color or dark gray in color, and that is what comes out, that is your package. Okay. And then what we do is we take this, we kind of shape it, trim it, form plating and all that stuff, and this is my, depending on the type of interconnections that we will have, this is how finally my plastic encapsulated package is going to look like. From outside it is very similar, except the material to a ceramic package, except that the material is different, but again that is also kind of a rectangular structure with these leads coming out. Okay. And then these are kind of branding and marking, you will have the chip number and all that, and then you send it out. Okay. So, this is how the package comes out finally. All right. So, again the different steps are, we start with the chip and the, I am just skipping this first one from the wafer. We start with the chip and the lead frame. Okay. So, the die attach method happens to the center, the die to the chip to the lead frame, then wire bonding from the chip to these leads in the lead frame, okay. And then this encapsulation, which is very important, which is one of the differentiating factors from a ceramic package, and then we will take this lead frame, we will bend it, trim it, plate it, etc., and then finally my package is done. Again, if you look at, if you have a memory card, you will be able to see, typically depending on what type of memory you have, you will be able to see some of these typically plastic, black colored or dark gray colored plastic encapsulated packages on this small memory card. Okay. All right. So, after plastic and ceramic packages and chip carriers, let us move on to something called a dual inline package, which is something we saw. Okay. It can be plastic, it can be ceramic, but what is important is this was the first package that was invented in the 1960s. At that time the chips were low wattage, fully encapsulated at that time when it was introduced. Later in the ceramic version also it is available. All right. And so, what comes out is, it is called dual inline because it comes, the interconnections come out from both sides, that is why dual, and then they are in series. So, that is why the inlined part comes in. Okay. All right. This picture also gives you some of these dimensions, these are all in inches by the way, and this is the structure. So, dual inline package is still a very common configuration that is used in many electronic products. What are the advantages? The pins and connections are very robust. It is an automated assembly. We will see assembly processes later, but these are very amenable to automation in assembly line. Okay. The width of pins is increased near the body, and as you can see here, if you look at this picture, the width close to the body is wider compared to the pins that come out. Okay. So, this kind of provides a shoulder, a strength at that location, and then these pins actually get into corresponding holes in the motherboard. So, these are some of the advantages. What are the disadvantages? So, if you look at these dimensions, these are pretty large. So, therefore, the IO count is pretty low. 100 mils is milli inch, okay, 1/1000th of an inch. So, 0.1 inch typically is the limit of the pitch between two successive leads. Okay. So, therefore, it is limited variability, limited number of connections and poor area efficiency. So, typically the amount of area, the footprint that is required, which is very very important, okay, the amount of space that your device, that your chip takes up in your motherboard, that is very important, by the way. When you come up with small packages and all small systems, the amount of space that you require to station a chip on the motherboard becomes very important. It is called real estate, okay. Just like land price is very very costly and land, so you want to have most of it in a limited piece of land. Similarly, in the motherboard also the space available is very small. At the same time, we want all features. So, therefore, we need packages which can have large number of IOs over a small area. Okay. So, that area efficiency for a dual inline package is not great, but then it is not expected also. Again, remember, this was the first package that was invented in the 60s. So, at that time this is just an emerging field. Okay. So, after that, of course, there has been refinements and advancements, but still today we have better designs, of course, but the dual inline package still remains a very popular choice and or very popular configuration. Okay. If I look at types of leads now, dual inline package, let us take a dual inline package itself and look at the types of leads. Okay. The first one is, as you see here, what we were seeing before. These leads come out in the form of, there is a shoulder next to the package, and then what you see is these pins go into corresponding holes in the motherboard. So, this is a pin in hole arrangement. Okay. So, typically, again I am probably jumping a little bit, we will cover this more when we go to motherboard, but over here itself you may appreciate that this pin has got into a corresponding hole, the inside surface of which is metallized. Okay. And these holes in the motherboard are connected to the wiring traces, okay, and this is how the connection is made. Okay. So, this is how, remember, we started with some of these contact points on the silicon. So, from the silicon the wire bonds were used to bring the connections to these leads, and then these leads go into this corresponding pinholes or pin in hole or through holes, and then that is how the connection is made to the wiring traces inside the motherboard. Okay. So, pin in hole is important, is common. Okay. The next one is what is called a gull wing type. So, here the configuration is in this form. The gull wing this is how it is, as you can see. What is the use here? What is the difference? Difference is these points that you see are no longer holes. These are not holes anymore, but these are pads. These are wiring traces, and then these are metallized pads on which this lead is going to be bonded, most likely with solder. Okay. So, these are not holes. The other one is J type leads. Okay. You will have again these pads attached at the end of this wiring trace, and the J and the lead is going to be bonded over here. Okay. Now, in this case the shape is in the form of a J. this was a metallized pad. So, this is how the connection is made. So, in either the Gullwing type or the J type, you do not have holes in the motherboard, plated holes in the motherboard, unlike the pin in hole arrangement. So, is there an advantage to that? You bet, because if you do not have holes, what happens? The reverse side of this board is also now available, and we can have probably a similar package attached on the underside of the motherboard as well. Okay. So, then you have a double sided board, clear. If you have holes, you cannot do that. All right. So, we will end with that, the overview of packages, and we will end today's lecture with that. So, what we studied as part of this, to recap, we started with looking at the types of ceramic packages and plastic packages, looking at their assembly processes as well. Okay. We saw that ceramic packages are expensive ones used in high end products. Plastic packages on the other hand are used more commonly in daily consumer electronic products that we use on day to day basis. But of course, reliability of a ceramic package is much more than plastic package, and so is the cost. Okay. And after that, we looked at the assembly processes, and then finally, we looked at the different kinds of leads that are used both in ceramic as well as plastic packages. There are pin in hole types, there are J types, there are Gullwing types, and in the ceramic parts we also saw there are lidless packages and so on and so forth. Okay. And somewhere in the middle, we talked a little bit about area efficiency, which becomes very important. Okay. Given a certain amount of area, how many interconnections can I have? Okay. So, this becomes very important because space on the motherboard comes for a premium. There is a limited space, and I want maximum number of components and connections to be made. Okay. So, we will discuss all this because the importance of this later as we look at different configurations. Okay. So, till then, till the next class, have a very nice day, and I hope you learned something new from these from the last two lectures. Thank you very much.